Good day, stat students. So today we're going to talk about section 6.1, and we're going to get into what's called probability distributions. And these are pretty important in statistics. So let's get into it. So first, before we talk about probability distributions, we have to talk about a random variable. So a random variable is a numerical measurement from an outcome of a random event. And so, to be honest with you, this is not much different than just your typical variable. Essentially, what's going on here is that the result of this variable was due to some random event. Okay, and so either it came from a random sample, or it came from doing a randomized experiment, because an experiment, things get randomized, right? And so you have this idea of a random variable, but it like I said, it's not very different from what we've learned before, other than now it's coming either from a random sample or an experiment. So you have two types of random variables. Either you have a discrete random variable or you have a continuous. And so in 6.1 we are going to concentrate on the discrete random variables, all right, and in 6.2 and we're going to concentrate on a continuous random variable. And this is a little weird as far as how the book was set up. 6.3 goes into a specific discrete random variable, and so I think the way we should handle this is that we're gonna go over 6.1, and then we're going to go to 6.3, because 6.3, like I just said, gets into a very specific discrete random variable that we have to learn. So I'm going to put those two together, back to back, I should say, 6.1 and 6.3, and then we'll head back to 6.2, the continuous stuff. All right, so that's probably how we're going to handle chapter 6. All right, so a word of warning: you have to keep the rules straight regarding discrete and continuous random variables. What you're going to find out is that there's slightly different rules with regards to the two, and so we have to keep them separate. We have to keep them straight, all right? Because believe it or not, once you learn one, it's almost the exact opposite for the other one, especially for one of the rules, all right? So you'll see. All right, so let's get into discrete random variable. So okay, so remember, these are variables that are usually a whole number that we can count, like 0, 1, 2, right? And so that's what we're going to be dealing with in 6.1 and also in 6.3. So probability distribution of a discrete random variable. What exactly is that? Well, what it does is that it lists all the values of x, assuming x is discrete, all right, along with the corresponding probabilities for each value of x, all right. And so once you see this is probably simpler than what it sounds like, all right. And really there's two basic rules here. One, all the probabilities have to be valid, and then two, the sum of all the probabilities has to add up to 1. So let's do this. I always try to think of things that you guys can relate to somewhat, and so let's do this. Let x be equal to the sum of a roll of a pair of 6-sided dice. So no Dungeons and Dragon dice or anything like that. All right. So we're rolling 2 dice. Okay, both are 6-sided. So like a roll in like Monopoly, okay, or another board game like that has 2 dice that are 6-sided, or if you will, a casino game. The casino game called craps. The whole game is based upon, and the payouts are based upon, the probability distribution that we're going to go ahead and develop. All right. Now here's the thing, is that we're not going to ask you to develop a probability distribution, but it's kind of cool to see this one because it's fairly easy to see how it would be developed. And like I said, we're very familiar with it, and some interesting and cool things kind of come from it. Well, it's cool to me anyways, all right? We'll see. So what we're going to do is we'll go ahead and Remember, the probability distribution has to list the values of x, and so the values of x will go here, all right? And because we're talking about dice and their combinations, we'll put the combinations here, okay? And then how many combinations we get, and then we can calculate the probability, all right? And so really a probability distribution, if you go back to the definition, really only involves this column and that column, all right? X and their corresponding probabilities, all right? But we need the other two to sort of help us to get to the probability. All right, so let's start with this. So what's the smallest value that you can get from a roll of two paired dice? Well, the lowest number that you can get on each dice is 1. And so the sum, okay, the smallest sum that you can get is 2. And so that would be, remember, an x is equal to the sum of a roll of a pair of 6-sided dice. So that's our lowest value, all right? And how many different ways could we do that? Well, the combination that we would have to roll is a 1 and a 1. That's it. So 1 on the one, 1 on the other. And so there's only one way of doing that, all right? We'll have to skip the probability, and for now we're going to have to fill in all the other ones, from, as far as x, all their combinations, and then their frequency, and then we can come back to the probability. So what's the next smallest value? 3, right? Notice it's discrete, right? 2, 3, 4, 5, so on and so forth. And what are the different combinations that we could do here? So there's actually 2 different ways of doing this. So you can have a 1 and a 2. So you can have a 1 on the first die and a 2 on the second die. Or you can have a 2 on the first die and a 1 on the second die. And so there's 2 ways of doing that. So we go to the next one. 4. So with 4, you can either roll a 1 and a 3, 2 and a 2, 3 and a 1. And there's 3 ways of doing that. So it looks like every time that we went up one number, it's gone. A number of combinations has gone up 1. Let's see if how long that continues. So here's 5. So with 5, you can roll it 1 and a 4, 2 and a 3, 3 and a 2, 4 and a 1. And there's 4 ways of doing that. How about, so it went up again, right? How about 6? 6, you can either roll a 1 and a 5, 2 and a 4, 3 and a 3, 4 and a 2, or 5 and a 1. And there's, 5 different combinations of doing that. All right, so 1, 2, 3, 4, 5. All right, we go to the next one. 7. We got 1 and a 6, 2 and a 5, 3 and a 4, 4, 3, 5, 2, 6, 1. 6 ways of doing that. Okay, so it looks like it's gone up every time. Let's see if it continues with 8. Now think about this for a second. What's the smallest number that you can get on one of the dice, and still get an 8? Well, it can't be 1 anymore, right? Because you can't get a 7 on the other one. And so what's the smallest number that you can get? The smallest number you can get is a 2, because the highest number that you can get is a 6. And so let's see what happens here. So with 8, notice here, 2 and a 6, 3 and a 5, 4 and a 4, 5 and a 3, 6 and a 2. So it actually went down from 7, all right? It went down 1, and we only have 5 combinations now. Let's see what happens next. So I went ahead and filled in the rest of them. So I filled in 9, 10, 11, and 12. Okay, and notice that it actually started going down again. Okay, and so I'll point something out to you. We can't figure out why this happened until chapter 7, but notice even for dice, what happens here with regards to these probabilities. And you can very much see it with regards to all the different combinations, that it looks like a nice bell-shaped curve, doesn't it? And so probabilities sort of take on a bell-shaped curve. That's kind of interesting. That's interesting to me anyways. But anyways, let's get back to our probability distribution. So how would we figure out these probabilities? Well, we would have to, there's 2 ways that you could go about it. You could either go ahead and count up all these frequencies, and that would turn out to be 36. All right. However, there is another way of doing this. Is that, think about it this way: is that you have 6 possibilities on one die, and you have 6 possibilities on another die. And so to figure out the total number of combinations there, you would multiply those two numbers together. 6 times 6 is 36, and so either way. But so you here the sum of all these frequencies is 36, and so then what does that mean with regards to the probability of getting a 2? Well, there's only one way of doing this out of a total of 36, and so I just hit the wrong button. That's okay. So now I'm going the right way. I just hit the button the wrong way. So so like I said, there's 36 different combinations here, all right? And so the probability of getting a 2, all right, there's just one way of doing that. So that would be 1 out of 36. And then you have all these other ones. So for the probability of getting a 3, it would be 2 out of 36, and so on and so forth, okay? And so here are all the probabilities, and if you added up all these probabilities and left, and I could care less about reducing fractions here, okay? That's not the point of the exercise here. I would just leave them over 36, all right? If you added up all these probabilities, guess what you're going to get? 1, okay? So, like I said, we can get rid of the combinations and the frequencies, and truly this would be the probability distribution for the sum or roll of 2 dice that are 6-sided. It lists all the values that x can take on. Notice it's discrete, okay, and their corresponding probabilities. There's your probability distribution, okay? So not that hard. All right, now we can do different things with this probability distributions. For instance, we could start asking questions, and we could start out very simple. We could ask, what is the probability that we roll a pair of dice and we get a 2 to show up, or what's the probability of getting a 3, or what's the probability of getting a 4? And so the very first question I ask is what's the probability of getting a 4? So you would just come here and say, okay, here's 4. Here's the probability of rolling a 4, and it would be 3 out of 36. All right. Now, homework might ask you to go ahead and change that into a proportion / decimal. Okay, if it asks you to do that, go ahead, round it properly to whatever decimal places they're asking. Or if they ask for a percentage, fine. Okay, but for here, we'll just leave it at 3 out of 36 and good enough. All right. All right. Let's continue. Now we can get a little bit more sophisticated. So here, I'm asking what is the probability that x is less than 4? Okay, probability that x is less than 4. So here, would we include 4? Would we include 4 in this? And the answer is no, we would not. Okay, with discrete, you have to pay attention to if there's a equal to sign there. Okay, so remember this is the less than sign, so we're saying what is the probability that x is less than 4? So what are the values that are less than 4? That would be 2 and 3. And so I used a little bit of shorthand here, okay, and I could have written out like this. I could have written these out, probability that x is equal to 2 plus the probability that x is equal to, that was supposed to be an x, equal to 3. All right, and could have written out like that, but I chose to simply go ahead and use a little shorthand here. And the shorthand is that we just drop, we understand that it's x is equal to, and so we just say probability of 2 plus probability of 3 in parentheses. So we go to our table, okay, here's the probability of 2, here's the probability of 3, and we get to add those together. And so that would turn out to be 3 out of 36. All right, so like I said, we have to pay attention to if we have equal to signs. Here we have the equal to sign, all right, and so what are we doing? We're going to include 4, so we have the probability of 2 plus 3 plus 4. Again, we just go to our table. 1 out of 36, 2 out of 36, 3 out of 36, and what are we going to do with those? Add them together, and we get 6 out of 36. So the probability of rolling a 2, basically what that's meaning is that what's the probability of rolling a 2 or a 3 or a 4? Okay, and that would be the same as rolling a 7, believe it or not. 3 out of 36. Okay, we can do greater than. And so notice I don't have the equal to sign down here, so this would be the probability that x is greater than 8. So what are the values greater than 8? We've got 9, 10, 11, 12. And so here they are right here. And what are we just going to do with those? We're going to add them up. So basically, what is this saying? What's the probability of getting a 9 or a 10 or 11 or a 12? Okay. And so we have 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36, and we add those up and we get 10 out of 36. Okay, happens if we throw the equal to sign in there. Well, if we throw the equal to sign in there, now we got to go ahead and include 8. So we've got 8, 9, 10, 11, 12. What are their corresponding probabilities? Here they are. All right, so we got 5 out of 36 plus 4 plus 3 plus 2 plus 1 out of 36. Okay, and we add that up and we get 15 out of 36. All right, so I showed you less than, I showed you less than or equal to, I showed you greater, I showed you greater than or equal to. The one that sometimes stumps students a little bit is when we have something like this, where x, okay, is a value between two numbers. Okay, remember what I told you is that when x sits in between two numbers like this is just our mathematical way of saying, hey, x is in between these two numbers. All right, those two numbers right there. And the only thing that you have to pay attention to is that, do we have the equal to sign here? Do we have the equal to sign there? All right. Excuse me. So if we have the equal to sign down here, we would include 4. If we have the equal to sign here, we would include 9. Now here, I didn't include the equal to sign in either one, did I? And so that means we are just going to go ahead and say, okay, what are the numbers in between 4 and 9? We're not going to include 4. We're not going to include 9. What would that be? 5 through 8. Okay? And so we should be adding up those probabilities right there. So 4 out of 36, 5 out of 36, 6 out of 36, 5 out of 36. We add those up. And it looks like, let's see, that looks like 20 out of 36 to me. Okay. All right. How about this one? Here, now before you look over here, why don't you try to think about what are we trying to say here? You give it some thought. Try to not look at the answer over here of the values of x. Okay. Ask yourself, okay, what are the values between 3 and 9? And do we want to include 3? Do we want to include 9? So what are the numbers between 3 and 9? That would be 4, 5, 6, 7, and 8. Do we include 3? Nope. Do we include 9? Yes, because we have the equal to sign. So we would include 4 through 9 on this one. So we should be including those probabilities right there. So 3 out of 36 plus 4 plus 5 plus 6 plus 4 plus 4 over 36, and you add them together, right? And let's see, that looks like 10, 20, 27 over 36 looks like to me. Okay? So, why don't you try this one? You try this one. All right. So, pause the video, get a piece of paper out, pencil. Hopefully you already have one out. Okay, those out. Get your calculator out if you need it. All right. And go ahead and try it. And once you have finished, go ahead and start the video again. So hopefully you've gone ahead and do that. All right. And so what do we? So x is sitting in between what? 5 and 10. Right. So we're going to include 6, 7, 8, 9. Are we going to include 5? Yes, because we have the equal to sign here. Are we going to include 10? No. So that would be 5 through 9. And so, so we have 5 through 9. Okay. And like I said here, sorry about that, 5 through 9. And so we would have 4 over 36 plus 5 plus 6 plus 5 plus 4 over 36. Okay. And so, let's see, that looks like 24 over 36 to me. And I added those up. Okay. That's the reason why I left them all over 36. And so so it was easy to add them up, because all of them would have a common denominator then. Okay? So hopefully you can use probability distribution, okay? And you're going to see probability distributions again in 6.3, okay? But we're going to get away from this example. We're going to get into an example that has less numbers to deal with, okay? And so here's the new example. Let's say there are 10 pieces of paper and each one has a number on it, all right? And so x is equal to the number on the piece of paper. Okay, and so there are 10 pieces of paper. There's one piece of paper that has a 0. There are 2 pieces of paper that have 1, 3 have a 2, and 4 have a 3. Okay, and so that's the data. Okay, 0, 1, 1, 2, 2, 2, 3, 3, 3, 3. All right. Let's call this the entire population. We only did this for 10 pieces of paper. Okay, and so let's go ahead and calculate the mean of x. Let's calculate mu. Why am I saying mu? Because I'm saying that this is for the entire population. Okay, this is for the entire population. All right. So since we have the data, we can use the formula that we're sort of used to, the summation of x divided by n. And so if you add these up here, so let's see. We have 2, right? 1 plus 1 is 2, 4, 6, 8. 11, 14, 17, 20. So we have 20 divided by how many numbers there are up here? That's 10, and we get 2. Okay? That should sound very familiar to you. Okay? You're probably asking, well, why did we do that? And hopefully you'll understand by the time we're done with 6.1 here. All right? Now, on the next slide, let's change the data into a probability distribution. All right? And that's actually should be fairly simple, all right? And so here are the values of x, and so we're going to put it into this table right here, okay? And that's where the probability distribution will go, all right? And so, what does the probability distribution do? List the values of x, and so what should be going in here? There should be going a 0, a 1, a 2, and a 3, because those are the possible values, okay? Then think about it like this, is that let's say we threw the 10 pieces of paper into a hat and we mixed it all up. What's the probability of choosing one piece of paper and we get a 0? What's the probability of getting a 1? What's the probability of getting a 2? What's the probability of getting a 3? Okay, and so how many different zeros are there? There's 1 out of 10. Okay, and so that would be 0.1. All right, does that make sense? So we got 1 out of 10 possibilities, 10 pieces of paper. Okay, what's the probability of getting a 1? Well, there we have 2 pieces of paper out of 10. That would be 0.2. All right, and then a 2, we have 3 pieces of paper. That would be 0.3. And then 3, we have 4 pieces of paper. That would be 0.4. It's as simple as that. There's your probability distribution for x. And what is this saying? That 0 shows up 10% of the time, or 0.1. 1 shows up 20% of the time. 2 shows up 30% of the time. 3 shows up 40% of the time. That's all the probability distribution is telling you, is how often these numbers show up, okay, in a random setting. Okay? Okay, so now, here's my question. Can we calculate the mean of x using just the probability distribution? Okay, so we are not going to use the raw data. Okay, we are going to just use, can we just use these values right here, all right, to calculate the mean of x? Remember, and what did we find out the mean of x was? It was equal to 2. Okay, but could we use just this information right here to figure out what is the mean of x? And the answer is yes. However, I have to stress this. Please pay attention to this line right here. You need a different formula than the summation of x divided by n. That will not work. All right, I have to deprogram you a little bit. Okay. Ever since you've learned how to calculate an average, a mean, you've always used the same formula. Okay, you've always used the same formula. You know why you always use the same formula? Because you were always given the data. Okay, you were always given the data. Okay, Well, what I have to sort of deprogram you is that in mathematics and statistics, there are a whole bunch of different ways of calculating a mean. Okay? It just depends on the situation that you are given. Okay? And you're going to see that throughout the semester here. Okay? So depending depending on the situation, you might have to use a different formula to calculate a mean, believe it or not. Okay, and you gotta understand that. So you're not going to always use the summation of x divided by n, and that will certainly not work here. All right, and so this right here is only used if you have the data. Okay, if you have the data like right here. Okay, that will not work here. All right, so we're gonna have to change it up. So to calculate the mean of x using the probability distribution of x, all right, what we're going to do is use a different formula, but it's a simple formula. It's not a hard formula. It's fairly straightforward, all right, and here it is. It's the summation of x. Now there is a multiplication sign here, okay, and so this is saying, now remember we have a summation sign here. Okay, we have a summation sign here, and so what does that mean? That there isn't just one x, there's multiple x's out there. And what do we got to do is that for each one of the x's, we have to multiply it by its corresponding probability. So all this is standing for is what? The probability of x. Okay, and so we're literally taking the value of x and multiplying it by its corresponding probability, and we're doing that for each one of the x's. And that's what I wrote down there. Is that this is saying sum of what? Take each value of x and multiply each one by their corresponding probability. Okay? And so remember, in the order of operations, you have to do multiplication first. So you're going to take each x and multiply it by its corresponding probability and do what with them? We're going to add them up. Okay? We're going to add them up. And so what we're going to have to do is we're going to have to make a new column here. Okay? See, here's the good thing, is that here are all the values of x, and here are their corresponding probabilities. Okay? And so all we have to do is, and there's your probability distribution for x, is that we have to go ahead and make another column here. All right? And call it x times p of x. Okay? X times its corresponding probability. All right? And so what are we going to do? We're going to start with the first x. Remember, you're going to do this for each one of the x's. This doesn't mean that there's just one x. There's multiple x's because we have a summation sign out there. All right. So we're going to start with the first x, multiply it by its what? Corresponding probability. So 0 times 0.1 is obviously 0. Then we go to the next one. We go to the next x. What are we going to do? We're going to take x, multiply it by its corresponding probability, and what do we get? We get 1 times 0.2 or 0.2. We go to the next one. 2 times 0.3, right? So all we're doing is multiplying across here, okay? And that would be 0.6. And then finally, 3 times 0.4, 1.2. So we did the hard part. We just did that portion of the formula. What's the last portion of the formula? Last part says, go ahead and add all those up. So if you add up 0 plus 0.2 plus 0.6, that's 0.8, plus another 1.2, you get 2. All right, so this is mu. All right, that is the mean of x. Okay, and so again, this is the formula to use when you have when you're trying to figure out the mean of x, but you are not given the raw data. You are given the probability distribution of x. So remember a few slides ago, and you don't have to look on this whole thing. I put it in red, but what I wanted you to focus in on is that when you had the raw data, okay, we used this formula right here, and what did we get for mu? We got 2, right? And when we went ahead and used the probability distribution of x and used the correct formula, what did we get? We got 2 for the mean of x. These should match up, okay? Actually, they have to, right? They're both calculated the mean of x. It's just that one is using the raw data, the other formula is using the probability distribution of x. Okay, and so So we're going to see that throughout the semester, is that there's different ways of calculating means. Okay, you just got to look at the situation that you got. All right, here, did you have the raw data or did you have the probability distribution of x? All right. All right, so a couple last things about this. Okay, when using this formula, please do not divide by anything. Okay, students are always tempted that, oh, I got to divide by n now. No. Notice here there is no n in the formula. Okay, there's no n in the formula. Please do not divide by anything. You know what this tells me? Is that since there's no n in the formula, it doesn't matter how many actual pieces of paper are in the hat. It doesn't matter if there's 10 pieces of paper in the hat or if there are a billion pieces of paper in the hat, as long as we know that 0 shows up 10% of the time, 1 shows up 20% of the time, 2 shows up 30% of the time, 3 shows up 40% of the time. Doesn't matter if there's 10 trillion pieces of paper. As long as we know that information there, okay, we know what the mean is going to be. It's going to be 2. Okay. Last thing, since this is what we would expect to happen in the long run, meaning if we did this experiment over and over and over again, so let's go back to just simply our 10 pieces of paper. We put the 10 pieces of paper in the hat, and we drew out a number, okay, and then we recorded that number, all right, and let's say it came out to be a 3. We threw the piece of paper back in the hat. We did it again. The next number that came out is a 1, and we took that piece of paper and we threw it back into the hat, and then we did it again, and we did it again, we did it again, and we wrote down all those all of our answers. You know, what was the number that we drew out of the hat? We went ahead and wrote those numbers down. If we did that a really long time, okay, what we would expect to happen is that the average would turn out to be 2. It's what we would expect in the long run for the average. All right, and so we can call the mean then what we can refer to it as an expected value. An expected value. So when you hear expected value or mean in statistics, they mean exactly the same thing. They're saying exactly the same thing. And so expected value of x is denoted with e with an x in parentheses. And so we could say then that the expected value of x is equal to mu, and it is equal to the summation of x times p of x if we have what? If we're working with the probability distribution of x. Okay? All right, so I think that ends this section here. So remember, we're going to jump over into 6.3 next. Thank you for your time.